Hi, I'm Thomas. Welcome to math class. We're looking at differential calculus applications. Today's application is linear approximations. The concept of linear approximations is taking the slope calculation for a line and applying that to estimate the change in a non-linear equation in output. Let's look at an example. Our function is the square root of x plus x. And I can take the derivative of this function to create a formula to calculate my slope at any given point on the original function. My derivative of square root of x is 1/2 times x to the power of negative 1/2, and the derivative of x is 1, which I can simplify to 1 over 2 times the square root of x plus 1. So to begin, I'm going to calculate the exact slope of the original function using my derivative at the x coordinate, or the x input, of 9. So if I input an x value of 9 into my derivative function, I end up with 1 over 2 times the square root of 9 plus 1, which simplifies to 1 over 6 plus 1, which is 7 over 6. So now what I know is that my slope at an input of 9 is 7 over 6. I also want to know what the exact coordinate is at that point on the curve. So with an input of 9 into my function, I have an output of square root of 9 plus 9, which equals 12. So at the point 9, 12 on the curve, the slope is 7 over 6. Now the slope is only 7 over 6 at this point on the curve. This is non-linear, so we don't have a constant slope. But my approximation is going to apply this slope to changes in x which are close to this point, changes in x which have a value for x close to 9. So my change in y, based on the approximation, is 7 over 6 times change in x. And traditional notation for the change in x is h. So I can say that the change in y, using the approximation, is 7 over 6 times h. So for this problem, if I'm asked to approximate the change in y for a change in x close to 9, this is the answer, 7 over 6 times h. Now let's see if this approximation is in fact accurate. Let's now apply the approximation to an actual estimate of a new output, or a new y, based on a new input or a new x. So let's test with an input value of 10. So according to my approximation, the input value of 10 is going to produce an output that is equal to the output for the function of 9 plus 7 over 6 times h. And h is my change in x, which in this case is a new x of 10 minus an old x of 9, which gives me 1. And so my estimate for the function of 10 is the output with the input of 9, or the function of 9 value of 12, which we calculated earlier, plus 7 over 6 times 1, which has a result of 13 and 1 over 6. Now that's an approximation. So what I want to do is see how close is that to the actual output when f is 10. So now let's use the actual function with an input of 10 and calculate our output. The function of 10 is the square root of 10 plus 10, which approximates to 13.162. Now comparing that to our answer in the approximation, 13 and 1/6, the approximate value of that approximation is 13.167. So we can see that the approximation got us very close to the actual output we calculated using the original function. Now, the more accurate answer comes from using the original function. But if you're asked to use approximation, then there are two contexts in which you might be using approximation. One is to calculate the estimated change in y given a change in x, and that for our scenario is 7/6 times h. You also might be asked to approximate a y value given a beginning x value, in our case 9, and an ending x value, or a new x value, in our case 10. And based on our approximation, we estimate the y value for an input of 10 to be 13 and 1/6. And we see that that is a very close estimate to the output that we calculate when we use the actual function. This concludes the topic linear approximations. I look forward to seeing you in the next lesson.